and welcome future statisticians to DepEd TV, a venue where you can be in one place virtually, even from different locations in reality. This is your teacher, Sophia Tricia Almasadas, and today I am together with another amazing teachers. Let us all welcome them.
Hello class! I am your teacher, Darlan May Almorigo.
Hi everyone, I am your teacher Justin Jane Orowala.
Hello, and I am your teacher, Zaire May Pamplona.
And today, we are your guide for an exciting and amazing stats venture.
So today, we are going to discuss Chapter 9, which is all about testing the difference between two means, two proportions, and two variances. And here is our learning objectives for today's discussion. At the end of the lesson, the students should be able to: first is to test the difference between sample means using the z-test. Second is to test the difference between two means for independent samples using the z-test. Third is to test the difference between two means for dependent samples. Fourth is to test the difference between two proportions. And the last one is to test the difference between two variances or standard deviations.
The basic concepts of hypothesis testing were explained in Chapter 8. With a z, t, and x squared test, a sample mean, variance, or proportion can be compared to a specific population mean, variance, or proportion to determine whether the null hypothesis should be rejected. In the comparison of two means, the same basic steps for hypothesis testing shown in Chapter 8 are used, and the z and t tests are also used. When comparing two means by using the t-test, the researcher must decide if the two samples are independent or dependent. The concepts of independent and dependent samples will be explained in section 9.2 and 9.3. The z-test can be used to compare two proportions as shown in section 9.4. Finally, two variances can be compared by using f-test as shown in section 9.5. The first subtopic for our lesson today is all about testing the difference between two means using the z-test. So, a z-test is a statistical test to determine whether two population means are different when the variances are known and the sample size is large. A z-test is a hypothesis test in which the z-statistic follows a normal distribution. A z-statistic or z-score is a number representing the result from the z-test.
Suppose a researcher wishes to determine whether there is a difference in the average age of nursing students who enroll in a nursing program at the community college and those who enroll in a nursing program at the university. In this case, the researcher is not interested in the average age of all beginning nursing students. Instead, he is interested in comparing the means of the two groups. His research question is: does the mean age of nursing students who enroll at a community college differ from the mean age of nursing students who enroll at the university? Here, the hypotheses are:
our null hypothesis is the first population mean is equal to the second population mean, and our alternative hypothesis is the first population mean is not equal to the second population mean, where the first population mean is equal to mean age of all beginning nursing students at the community college, and the second population mean is equal to the mean age of all beginning nursing students at the university. Another way of stating the hypothesis for this situation is our null hypothesis is the first population mean minus the second population mean is equal to 0, and the alternative hypothesis is the first population mean minus the second population mean is not equal to 0. If there is no difference in population means, subtracting them will give a difference of 0. If they are different, subtracting will give a number other than 0. Both methods of stating hypotheses are correct. However, the first method will be used in this book.
Assumptions for the z-test to determine the difference between two means. Number 1, both samples are random samples. Number 2, the samples must be independent of each other. That is, there can be no relationship between the subjects in each sample. And number 3, the standard deviations of both populations must be known. And if the sample sizes are less than 30, the populations must be normally or approximately normal distributed. The theory behind testing the difference between two means is based on selecting pairs of samples and comparing the means of the pairs. The population means need not be known. All possible pairs of samples are taken from populations. The means for each pair of samples are computed and then subtracted, and the differences are plotted. If both populations have the same mean, then most of the differences will be 0 or close to 0.
Occasionally, there will be a few large differences due to a change alone, some positive and others negative. If the differences are plotted, the curve will be shaped like a normal distribution and have a mean of 0 as shown in figure 9.1. The variance of the difference of the first sample mean minus the second sample mean is equal to the sum of the individual variances of first sample mean and second sample mean. So, to get that, let's take a look at the formula given below. The formula for the z-test for computing two means from independent population is shown in the figure. This formula is based on the general form of test value is equal to the observed value minus expected value over standard error, where the first sample mean minus the second sample mean is the observed difference and the expected difference is the first population mean minus the second population mean is 0. When the null hypothesis is the first sample population mean is equal to the second population mean, since that is equivalent to first population mean minus the second population mean is equal to 0. Finally, we will derive the standard error of the difference, which is shown in the formula below. In the comparison of two sample means, the difference may be due to chance, in which case the null hypothesis will not be rejected and the researcher can assume that the means of the populations are basically the same. The difference in this case is not significant. To see further, see the figure 9.2a. On the other hand, if the difference is significant, the null hypothesis is rejected and the researcher can conclude that the population means are different. See the figure 9.2b. Shown here in the figure 9.2 is the hypothesis testing situations and the comparison of means. So, this test can be one-tailed using the following hypothesis. So, let's take a look at the table presented and discuss the steps used to solve this. In able to solve this, here are the steps. Step 1. State the hypothesis and identify the claim. Step 2. Find the critical values. Step 3. Compute the test value. Step 4. Make the decision. And step 5. Summarize the results.
Now let's have an example. A survey found that the average hotel room rate in New Orleans is $88.42 and the average room rate in Phoenix is $80.61. Assume that the data were obtained from 2 samples of 50 hotels each and that the standard deviations of the populations are $5.62 and $4.83, respectively. At the significance level of 0.05, can it be concluded that there is a significant difference in the rates? Following the steps for hypothesis testing using the traditional method, our step 1 is to state the hypothesis and identify the claim. Our null hypothesis for this problem is mu sub 1 equals to mu sub 2, and our alternative hypothesis is mu sub 1 not equals to mu sub 2. Next step is we're going to find the critical values. Since our significance level is at 0.05 and this is a two-tailed test, our critical values will be positive 1.96 and negative 1.96. The third step is to compute the test value using the formula z equals to x bar sub 1 minus x bar sub 2 minus to the difference of mu sub 1 and mu sub 2 all over the square root of sigma squared sub 1 divided by n sub 1 plus the sigma squared sub 2 divided by the n sub 2. And we are just going to substitute our values or the given values. So 88.42 minus 80.61 in close parentheses minus 0. The 0 is our mu sub 1 and mu sub 2. All over the square root of 5.62 squared divided by 50 plus 4.83 squared divided by 50. This would result to 7.45. Now the fourth step is we are going to make the decision. Since our test value 7.45 is greater than our critical value 1.96, we are going to reject the null hypothesis at the significance level of 0.05. This will be our diagram. As you can see, our test value positive 7.45 is in the critical region, which means that there is enough evidence to support the claim that the means are not equal. Hence, there is a significant difference in the rates. Moving on, to find the p-values for this test, it can be determined by using the same procedure shown in the previous chapter, chapter 8 in section 2. For example, if the test value for a two-tailed test is 1.40, then the p-value obtained from table E is 0.1616. This value is obtained by looking up for the area for z equals to 1.40, which is 0.9192. Then 0.9192 is subtracted from 1.00 to get 0.0808. Finally, this value is doubled to get 0.1616 since the test is two-tailed. If the significance level is at 0.05, the decision would be not to reject the null hypothesis, since our p-value is greater than the significance level. Note that the p-value method for hypothesis testing for this chapter, chapter 9, also follows the same format as stated in chapter 8. The steps are reviewed here. Our step 1 is to state the hypothesis and identify the claim. Step 2 is to compute the test value. Third step is to find the p-value. Fourth step is to make the decision. And finally is to summarize the results. Let's have an example. A researcher hypothesizes that the average number of sports that colleges offer for males is greater than the average number of sports that colleges offer for females. A sample of the number of sports offered by colleges is shown. At the significance level of 0.10, is there enough evidence to support the claim? Assume that sigma sub 1 and sigma sub 2, or our two population variances, is 3.3. Now the first step is we're going to state the hypothesis and identify the claim. Our null hypothesis will be mu sub 1 equals to mu sub 2, and our alternative hypothesis will be mu sub 1 is greater than mu sub 2. Next step is to compute for the test value, but first, using your calculator and recall the formula from chapter 3, find the mean for each data set first. Now, the sample mean for the males will be 8.6 and for the females will be 7.9, and remember our population variance is 3.3. Now substitute these values to the formula. So 8.6 minus 7.9 in close parentheses minus 0 all over the square root of 3.3 squared divided by 50 plus 3.3 squared divided by 50. This results to 1.06. Now, third step is to find the p-value. For our test value 1.06, the area is 0.8554, and 1 minus 0.8554 is equals to 0.1446. Therefore, our p-value is 0.1446. Now, next step is to make the decision. Since our p-value is larger than the significance level, that is 0.1446 is greater than 0.10, the decision is not to reject the null hypothesis. Now summarize the results, which is there is not enough evidence to support the claim that colleges offer more sports for males than they do for females. Sometimes, in some cases, the researcher is interested in testing a specific difference in mean other than 0. For example, he or she might hypothesize that the nursing student at a community college are on average 3.2 years older than those at a university. In this case, the hypotheses are, our null hypothesis will be mu sub 1 minus mu sub 2 equals to 3.2, and our alternative hypothesis will be mu sub 1 minus mu sub 2 is greater than 3.2. The formula for the z-test is still the formula that we used from the previous slides, but this time, mu sub 1 minus mu sub 2 is the hypothesized difference or expected value. In this case, mu sub 1 minus mu sub 2 is equals to 3.2. Confidence intervals for the difference between two means can also be found. When you are hypothesizing a difference of 0, if the confidence interval contains 0, the null hypothesis is not rejected. If the confidence interval does not contain 0, the null hypothesis is rejected. Confidence intervals for the difference between two means can be found by using this formula. Mu sub 1 minus mu sub 2 is greater than x sub 1 minus x sub 2 in close parenthesis minus the critical value multiplied by the square root of sigma squared sub 1 over n sub 1 plus sigma squared sub 2 over n sub 2, but lesser than 2x sub 1 minus x sub 2 in close parenthesis plus the critical value multiplied by the square root of sigma squared sub 1 divided by n sub 2 plus sigma squared sub 2 divided by n sub 2. Now let's have an example. Find the 95% confidence interval for the difference between the means for the data in example 9.1, the example that we have previously. Now we are going to substitute the values from the example 9.1 in the formula using the critical value 1.96. So 88.42 minus 80.61 minus 1.96 multiplied by the square root of 5.62 squared over 50 plus 4.83 squared over 50, and that equals to 5.76. While 88.42 minus 80.61 plus 1.96 multiplied by the square root of 5.62 squared over 50 plus 4.83 squared over 50 is equals to 9.86. Hence, our mu sub 1 minus mu sub 2 is greater than 5.76 but lesser than 9.86. Since the confidence interval does not contain 0, the decision is to reject the null hypothesis, which agrees with the previous result. And that ends section 1. I hope that you learned something from this section.
Hello, future educators! So I hope you've learned something in testing the difference between two means using the z-test that was discussed by Ms. Masadas. In her discussion in section 9.1, the z-test was used to test the difference between two means when the population standard deviation were known and the variables were normally or approximately normally distributed, or when both sample size were greater than or equal to 30. In many situations, however, these conditions cannot be met, that is, the population standard deviation are not known. In these cases, a t-test is used to test the difference between means when two samples are independent and when the samples are taken from the two normally or approximately normally distributed population. Now, the next subtopic of chapter 9, or the second section of our lesson today, will be all about testing the difference between two means of independent samples using t-test. The independent sample t-test. The independent sample t-test compares the mean of two independent groups in order to determine whether there is a statistical evidence that associated population mean are significantly different. The independent samples t-test is a parametric test. This test is also known as independent t-test. The independent sample t-test is commonly used to test the following. First is to test the statistical difference between the means of two groups. Second is to test the statistical difference between the means of two intervention. And third is to test the statistical difference between the means of two change scores. Note, the independent samples t-test can only compare the means of two and only two groups. It cannot make comparison among more than two groups. If you wish to compare the means across more than two groups, you will likely want to run an ANOVA. In getting the difference between two means of independent sample using t-test, we're going to use this formula. Variance are assumed to be unequal. Muna nga ang yahang kuan usaan pagkuha sa t-value. Then, where the degrees of freedom are equal to the smaller of n sub 1 minus 1 or n sub 2 minus 2. There is different formula for the t-test for comparing two means from independent population with equal variance. To determine whether two sample variance are equal, the researcher can use the f-test. Note, however, that not all statisticians are in agreement about using f-test before using t-test. So, dili tanang statistician ang mi-agree ani. From belief that conducting the F and T test at the same level of significance will change the overall level of significance of the T test. The reasons are beyond the scope of this textbook. Because of this, we will assume that sigma sub 1 is not equal to sigma sub 2 in this textbook. Now, let's try this problem. The average size of a farm in Indian Country, Pennsylvania is 191 acres. The average size of farm in Green Country, Pennsylvania is 199 acres. Assume the data were obtained from two samples with standard deviation of 38 and 12 acres respectively, and the sample size of 8 and 10 respectively. Can it be concluded at A is equal to 0.05 that the average size of the farm is in the two countries is different? So assume the population are normally distributed. So in finding this, we need to follow the 5 steps that was discussed last week. So first step, we need to state the hypothesis and identify the claim. So unsa man ang ihang claim, ani nga problem? So kanino maoning ang iyahang nga claim, ani nga problem. Now, let's proceed to step 2. So the step 2 is find the critical value. Since the test is two-tailed, A is equal to 0.05. And the variance are unequal, the degrees of freedom are smaller of n sub 1 minus 1 or n sub 2 minus 1. In this case, the degrees of freedom are 8 minus 1 is equal to 7. Hence, from table F, the critical values are negative 2.365 and positive 2.365. Next step is step 3. So the step 3 is find the t value or the test value. So in finding the test value na ay formula. So atong gamiton ang formula. So this test value is equal to observed value minus expected value over standard error. So pila man ang unsa man nga mga numbers ang atong gamiton. Atong gamiton tong 191 o 191 ba to? 191 o 199. So, T is equal to 191 minus 199 minus 0 over the square root of 38 squared over 8 plus 12 squared over 10. So, if you namoy calculator, so you can calculate it if nga ang iyang ng answer is negative 0.57. Now, we're down to fourth step. So, the fourth step is make decision. So, in this problem, our decision is do not reject the null analysis. As you can see in the figure, no. So, step 5, summarize the result. So, what is the result? So, aning problem, ang iyang result is there is not enough evidence to support the claim that the average size of farms is different. Nga, dili magkapareha ang average size sa ilahang farm. Now, let's proceed to the confidence interval from the difference between two means. Formula for the T confident interval for the independence between two means from the independent population with an equal variance. So, kani nga formula ang ato ang gamiton. So, variance is assumed to be unequal. Parehas sa pagkuha sa t-test, ang variance is gi-assume gihapon nga unequal. So, kani nga formula nga ato ang gamiton. Now, let's try this problem. So, find the 95% confidence interval of the difference between the means of the data in example 9.4. So, ang example nga katong farm size. Ato ang pangitaon. So, solution. Kaning nasa ubos, mauni ang solution sa pagkuha sa 95 confidence interval for the difference between the mean of the data in example 9.4. In many statistical software packages, a different method is used to compute the degrees of freedom in this t-test. They are determined by formula. So, kani nga formula nga nakaito. Mauni nga formula ang gamiton. So, this formula is not be used in this textbook. Wala siya gamitan nga textbook. There are actually two different options for the use of test. One option is used when the variance of the population are not equal, if not dili siya equal. And the second option is used when the variance are equal, if ang kaduhang option kay og equal na. So, to determine whether two sample variances are equal, the researcher can use an F-test, as shown in section 9.5. So, as makita na to sa section 9.5 na. Nya, kung when the variances are assumed to be equal, this formula is used. Kani nga formula mo ni ang ato ang gamiton if ang variance kay assumed to be equal. So, this lang use and follows the format of t-value. So, ang t-value or test value. So, test value is equal to unsa gani ang test value, unsa pag sa test value, unsa equivalent sa test value. So, ang test value is equal to observed value minus expected value over the standard errors. For the numerator, the terms are the same as the previously given formula. However, a note of explanation is needed for the denominator of the second test statistic. Since both population are assumed to have the same variance, the standard error is computed with what is called a pooled estimate of a variance. So, unsa man ang pooled estimate variance? So, ang pooled estimate of variance is a weight average of the variance using two sample variances and the degrees of freedom of each variance as the weights. Again, since the algebraic derivation of the standard error is somewhat complicated, it is omitted. But note, Note na to nga, however, that not all statisticians, dili tanan statisticians, not all statisticians are in agreement about using the F-test before using the T-test. Dili tanan statistician nga mugamit ka og F-test if gagamit na pug ka og T-test. Some believe that conducting the F-test F and T-test at the same level of significance will change the overall of the significance of the test. These reasons are beyond the scope of this textbook. Because of this, we will assume that sigma sub 1 is not equal to sigma sub 2 in this textbook.
In section 2, where teacher Darlene have discussed, the t-test was used to compare two sample means when the samples are independent. In this section, a different version of t-test is explained. This version is used when the samples are dependent. So our third subtopic will be all about testing the difference between two means for dependent samples. Samples are considered to be dependent samples when the subjects are paired or matched in some way. Or in other words, when each member of one sample is related or corresponds to a member of other sample. An example of this is the weight of individuals before going on a diet and the weight of those same individuals after 10 weeks of dieting. Dependent sample are often referred to as paired samples or matched samples. When the samples are dependent, a special t-test for dependent means is used. This test employs the difference in values of the matched pairs. And we use the symbol mu sub d, and we assume that mu sub d equals 0. The usual pairing of hypotheses are as follows: with equals 0 and less not equal 0 paired, equals 0 and less than 0 paired, and equals 0 and greater than 0 paired together, where mu sub d is the symbol for the expected mean of the difference of the matched pairs. The general procedure for finding the test value involves several steps. First step is to find the differences of the values of the pairs of data. Using this formula, d equals x sub 1 minus x sub 2, where x sub 1 and x sub 2 are the two samples. Second is to find the mean of the differences denoted by d bar using the formula d bar equals to the sum of d divided by n, where n is the number of data pairs. Third step is to find the standard deviation denoted by s sub d of the differences using the formula s sub d equals to the square root of n multiplied by the sum of d squared minus the sum of d in close parentheses squared over n multiplied by n minus 1. Fourth step is to find the estimated standard error of the differences, which is s sub d bar equals to s sub d over square root of n. Finally, is to find the test value using the formula t, or the test value is equals to d bar minus mu sub d over s sub d divided by the square root of n, with the degree of freedom n minus 1. The formula in the final step follows the basic format of test value equals to observed value minus expected value over standard error, where the observed value is the mean of the differences. The expected value mu sub d is 0 if the hypothesis is mu sub d equals 0. The standard error of the difference is the standard deviation of the difference divided by the square root of the sample size. Both populations must be normally or approximately normally distributed. Now let's have an example. A physical education director claims by taking a special vitamin, a weightlifter can increase his strength. 8 athletes are selected and given a test of strength using the standard bench press. After 2 weeks of regular training supplemented with the vitamin, they are tested again. Test the effectiveness of the vitamin regimen at the significance level of 0.05, and each value in this data represents the maximum number of pounds the athlete can bench press. Assume that the variable is approximately normally distributed. So here is the given table For the first row is our subjects, the athletes. We have 8 subjects. And the second row is the before weights of the athlete, or the X sub 1. And the third row is the after weights of the athletes, or the X sub 2. And to follow the steps at the general procedure for testing the difference between two means for dependent variables, the step 1 is to state the hypothesis and identify the claim. For the vitamin to be effective, the before weights must be significantly less than the after weights. Hence, the means of the differences must be less than 0. So our hypothesis is mu sub d equals 0 and mu sub d less than 0. And that is our claim. That is the claim. Second step is to find the critical value. The formula for the degrees of freedom is n-1. In this case, we have n equals 8. So 8 minus 1 equals to 7. The critical value for a left-tailed test with significance level of 0.05 is negative 1.895. How did we get negative 1.895? Using this table, we will be able to find the critical values of t for one-tailed test. Critical value is 1.895. And since it is a left-tailed test, it will become a negative. So negative 1.895. Next step is to compute the test value. First, we are going to make a table. The first column is the before weights, or the first sample. The second column is the after weights of the athletes. And the third column, or column A, is the difference between the before weights and the after weights, or X sub 1 minus X sub 2. And the fourth column, or the column B, is the squared of our differences between the before weights and the after weights. Next step is to find the differences. So, unsa ganitong formula sa differences? D equals to X sub 1 minus X sub 2. We are just going to subtract X sub 1, which is 210, minus 219, which is the X sub 2, and it will be equal to negative 9. 230 minus 236 equals to negative 6, and so on. And lastly, we are going to add these differences to solve for the sum of D. So the sum of D is equals to negative 19. Then, we are going to find the mean of the differences using the formula D bar equals the sum of D divided by the N. So the sum of D is negative 19, and our N is 8. So negative 19 divided by 8 is equals to negative 2.375. And next step is to square the differences. So negative 9 squared is equals to 81, negative 6 squared is equals to 36, 3 squared is equals to 9, and so on. And we are going to add these to come up with the sum of D squared, 209. And now we are just going to input our answers to the table. And here it is. So we already now have the sum of D and the sum of D squared. Next step is to find the standard deviation of the differences using the formula. Now we are just going to substitute the values. The square root of 8 multiplied by 209 minus negative 19 squared over 8 multiplied by 8 minus 1. It will become square root of 1672 minus 361 divided by 56, and that results to 4.84. The last step to find the test value is to use the formula for finding the test value. T equals to D bar minus mu sub D over S sub D divided by the square root of N. We are going to substitute value for D bar, which is the negative 2.375, and mu sub D equals to 0 over our S sub D is 4.84 divided by the square root of N, which is 8. And that results to negative 1.388. The fourth step is to make the decision. Since our test value negative 1.388 is less than to our critical value negative 1.895, the decision is not to reject the null hypothesis at the significance level of 0.05. And here is our diagram. As you can see, our test value falls outside the critical region, negative 1.895, which means that there is not enough evidence to support the claim that the vitamin increases the strength of weightlifters. Let's have another example. Just like what we did from the previous example, the step 1 is we're going to state the hypothesis and identify the claim. If the diet is effective, the before cholesterol levels should be different from the after levels. Hence, our hypothesis is mu sub d equals 0 and mu sub d not equal to 0, and that is the claim. Second step is to find the critical value. Since our n is 6 and the formula for degrees of freedom is n minus 1, so 6 minus 1, we have the degrees of freedom of 5. At the significance level of 0.10, our critical values are positive and negative 2.015. And since it is a two-tailed test, we have two critical values, the positive 2.015 and the negative 2.015. Next is to compute the test value. First, we must make a table. Just like the previous example, it has 4 columns. Next step is to find the differences. So the difference between 210 and 190 is 20, 235 and 170 is 65, and so on. The sum of our differences is 100. Next step is to find the mean of the differences using the formula d bar equals to the sum of d divided by n. Our sum of d is 100 and our n is 6, so 100 divided by 6 is equals to 16.7. Then we're going to square the differences. So 20 squared equals to 400, 65 squared is equals to 4,225, and so on. And lastly, we are going to find the sum of d squared, which is equals to 4,890. And next is we are just going to input our results to the table. And here how it looks. We now have the sum of d, which is the 100, and the sum of d squared, which is for 4,890. Next step is to find the standard deviation of the differences using the formula. We're just going to substitute the values. So the square root of 6 multiplied by 4,890 minus 100 squared all over 6 multiplied by 6 minus 1 equals to the square root of 29,340 minus 10,000 divided by 30, which equals to 25.4. Lastly is to find the test value using the formula. So 16.7 minus 0 all over 25.4 divided by the square root of 6 is equals to 1.610. Fourth step is to make the decision. Since our test value 1.610 is in the non-critical region, or it falls outside our critical value 2.015, positive and negative 2.015, the decision is to not reject the null hypothesis. That means that there is not enough evidence to support the claim that the mineral changes a person's cholesterol level. For us not to forget the procedure in testing the difference between two means for dependent variables, here is the procedure table. You can pause this video and take a screenshot of it. Now moving on, the p-values for the t-test are found in table F. For a two-tailed test with degree of freedom 5 and t equals to 1.610, the p-value is found between 1.476 and 2.015. Hence, our p-value is greater than 0.10 but lesser than to 0.20. Thus, the null hypothesis cannot be rejected at the significance level of 0.10. We use again the t distribution table. So we have our degree of freedom 5 and t equals to 1.610. We are going to find the closest value of 1.610. Since the closest value is 1.476 and 2.015, and that would be our p-values. If a specific difference is hypothesized, this formula should be used. T equals to d bar minus mu sub d all over s sub d divided by the square root of n. This formula is just the same with the formula that we used from the previous slides, but this time mu sub d refers to the hypothesized difference. For example, if a dietitian claimed that people on a specific diet will lose an average of 3 pounds in a week, the hypotheses are, our null hypothesis will be mu sub d equals to 3, and our alternative hypothesis will be mu sub d not equals to 3. The value 3 will be substituted in the test statistic formula for mu sub d. Now let's have the confidence interval for the mean difference. Confidence intervals can be found for the mean differences with this formula, where mu sub d is greater than d bar minus the critical value times the standard deviation divided by the square root of n, but less than d bar plus critical value times standard deviation divided by the square root of n, where df or the degree of freedom is equals to n minus 1. Let's have an example. Find the 90% confidence interval for the data in example 9.7. Remember that our mean differences from the previous example is equals to 16.7. Our critical value is equals to 2.015. Our standard deviation is equals to 25.4 and our n is equals to 6. Now substitute these values into the formula. Now we have 16.7 minus 2.015 times 25.4 over the square root of 6, which will be equal to negative 4.19. And 16.7 plus 2.015 times 25.4 divided by the square root of 6 is equals to 37.59. So our final answer is mu sub d is greater than negative 4.19 but less than 37.59. Since 0 is contained in the interval, the decision is to not reject the null hypothesis mu sub d equals to 0. And now that ends section 3. I hope that you understand my explanation and you will be able to apply what you have learned from this section to our activities.
Hi, I'm Zairme Pamplona, and I'll be the one to discuss about the testing difference between two proportions. So, the z-test with some modification can be used to test the quality of two proportions. For example, a researcher might ask, is the proportion of men who exercise regularly less than the proportion of women who exercise regularly? Is there a difference in the percentage of students who own a personal computer and the percentage of non-students who own one? Is there a difference in the proportion of college graduates who can pay cash for purchases and the proportion of non-college graduates who pay cash? Recall from chapter 7 that the symbol of p hat is the sample of proportion used to estimate the population proportion denoted by p. For example, if in a sample of 30 college students, 9 are on probation, then the sample proportion is p hat is equal to 9 over 30 or 0.3. The population proportion p is the number of all students who are on probation divided by the number of students who attend the college. The formula for is p hat equals to x over n, where x is the number of units that possess the characteristic of interest, and n is the sample of size. When you are testing the difference between two populations proportion p sub 1 and p sub 2, the hypothesis can be stated those. If no difference between the proportion is hypothesized. So H null hypothesis colon p sub 1 equals p sub 2 and alternative hypothesis colon P sub 1 is not equal to P sub 2, or null hypothesis colon P sub 1 minus P sub 2 equals 0, and alternative hypothesis colon P sub 1 minus P sub 2 is not equal to 0.
Similar statement using less than or greater than in the alternate hypothesis can be formed for one-tilde test. For two proportions, p hat sub 1 equals x sub 1 over n sub 1 is used to estimate p sub 1, and p hat sub 2 equals x sub 2 over n sub 2 is used to estimate p sub 2. The standard error of the difference is standard p hat sub 1 minus p hat sub 2 equals square root of standard squared p sub 1 plus standard squared p sub 2 equals p square root of p sub 1 q sub 1 over n sub 1 plus p sub 2 q sub 2 over n sub 2, where the standard squared p sub 1 and standard squared p sub 2 are the variance of the proportions q sub 1 equals 1 minus p sub 1, q sub 2 equals 1 minus p sub 2, and the n sub 1 and n sub 2 are the respective sample sizes. Since p sub 1 and p sub 2 are unknown, a weighted estimate of p can be computed by using the formula in this formula below. And q equals 1 minus p. This weighted estimate is based on the hypothesis that p sub 1 equals p sub 2. Hence, p is a better estimate than either p hat sub 1 or p hat sub 2, since it is combined average using both p sub 1 and p sub 2. Since p hat sub 1 equals x sub 1 over n sub 1 and p hat sub 2 equals x sub 2 over n sub 2, p can be simplified too in this formula below. Finally, the standard error of the difference in terms of the weighted estimate is in this, as you can see in this formula. The formula for the test value is shown next. Formula for the z-test for comparing two proportions, where the z equals p hat sub 1 minus p hat sub 2 minus p sub 1 minus p sub 2 over square root of p and q times 1 over n sub 1 plus 1 over n sub 2, where the p is x sub 1 plus x sub 2 over n sub 1 plus n sub 2, and q is equal to 1 minus p, and the p hat sub 1 will equal x sub 1 over n sub 1, and the p hat sub 2 equals x sub 2 over n sub 2. This formula follows the format: test value equals to observed value minus expected value over standard error. There are two requirements for use of the z-test. 1. The sample must be independent of each other. And 2. N sub 1, p sub 1, and n sub 1, q sub 1 must be 5 or more. And n sub 2, p sub 2, and n sub 2, q sub 2 must be 5 or more. Example: vaccination rates in nursing homes. In the nursing home study mentioned in the chapter Opening Statistic today, the researcher found that 12 out of 34 small nursing homes had a resident vaccination rates of less than 80%, while 17 out of 24 large nursing homes had a vaccination rate of less than 80%. At a 0.05 test that claimed that there's no difference in the proportions of the small and large nursing homes with a resident vaccination rate of less than 80%. Solution: Let P hat sub 1 be the proportion of the small nursing home with a vaccination rate of less than 80%, and P hat sub 2 be the proportion of the large nursing home with a vaccination rate of less than 80%. Then the P hat sub 1 is equal to 0.35, and the P is 0.5, and Q is 0.5, and P hat sub 2 is 0.71. So now, follow the step in the hypothesis testing. Step 1. State the hypothesis and identify the claim. So the null set, a null hypothesis, colon P sub 1 equals P sub 2 claim. So step 2, find the critical values since alpha is 0.05 and the critical values are positive 1.96 and negative 1.96. So step 3, compute the test value. So P hat sub 1 is 0.35 minus the P hat sub 2 is 0.71, and the P hat sub 1, P sub 1 minus P sub 2 is 0, over the square root of 0.5 times 0.5 times 1 over 34 plus 1 over 24 is equals to negative 0.36 over 0.1333 equals to negative 2.7. So step 4, make the decision reject the null hypothesis since negative 2.7 is less than the negative 1.96. Step 5. Summarize the result. There is enough evidence to reject the claim that there is no difference in the proportions of small and large nursing homes with a resident vaccination rate of less than 80%. As you can see, the figure 8, critical and test value, for example, 99, 9 and 9. Another example. In a sample of 200 workers, 45% said that they missed work because of personal illness. So 10 years ago, in a sample of 200 workers, 35% said that they missed work because of personal illness. At alpha equals to 0.01, is there a difference in the proportions? So the solution is, since the statistic are given in percentages, P hat sub 1 equals 45% or 0.45 and P hat sub 2 equals 35% or 0.35. To compute the P, you must find the X sub 1 and X sub 2. So the X sub 1 is P hat sub 1 is the 0.45 and N sub 1 is 200. So multiply the 0.45 times the 200 equals to 90. So the X sub 2, the P hat sub 2 is 0.35 and N sub 2 is 200. Multiply, it is equals to 70. P equals to X sub 1 plus X sub 2 or N sub 1 plus N sub 2 equals to 90 plus 70 over 200 plus 200 equals to 160 over 400 equals 0.4. So the Q is equals to 1 plus P equals 1 minus 0.4 equals 0.6. So step 1, state the hypothesis and identify the claim. So the alternatives hypothesis colon P sub 1 is not equal to P sub 2. Find the critical value since mean is 0.01 and the critical values are positive 2.58 and negative 2.58. Compute the test value. So the answer is 2.04. The p-value for the difference of proportions can be found from Table E, as shown in Section 9-1, for example 9-10, 3.99 is beyond 3.09. Hence, the null hypothesis can be rejected since the p-value is less than 0.001. The formula for the confidence interval for the difference between two proportions is shown next. Solution. P hat sub 1 is equal to 0.35. P hat sub 2 equals to 0.71. Q hat sub 1 is equal to 0.65 and Q hat sub 2 is equal to 0.29. Substitute in the formula. As you can see, the P hat sub 1 is 0.35 and the minus to P hat sub 2, which is 0.71, minus the Z test 1.96 square root of 0.35 times 0.65 over 34 plus 0.71 times 0.29 over 24, and P sub 1 minus P sub 2 is equal 0.35 of minus 0.71 plus 1.96 square root of 0.35 times 0.65 over 34 plus 0.71 times 0.29 over 24. So this is the result, which is negative 0.602, and P sub 1 minus P sub 2 is less than the negative 0.118. Since 0 is not contained in the interval, the decision is to reject the null hypothesis.
That is all about the test, the difference between two proportions.
In addition to comparing two means, statisticians are interested in comparing two variances or standard deviations. For example, is the variance in the temperatures for a certain month for two cities different? In another situation, a researcher may be interested in comparing the variance of the cholesterol of men with the variance of the cholesterol of women. Now for the last subtopic or the last section for our lesson today, it will be testing the difference between two variances. For the comparison of two variances or standard deviations, an F-test is used. The F-test should not be confused with the chi-square test, which compares a single sample variance to a specific population variance as shown in Chapter 8. If two independent samples are selected from two normally distributed populations in which the variances are equal, sigma squared sub 1 equals to sigma squared sub 2, and if the variances s squared sub 1 and s squared sub 2 are compared as s squared sub 1 all over s squared sub 2, the sampling distribution of the variances is called the F distribution. These are the characteristics of the F distribution. First, the values of F cannot be negative because variances are always positive or zero. Second, the distribution is positively skewed. Third, the mean value of F is approximately equal to 1. And the last characteristic is that F distribution is a family of curves based on the degrees of freedom of the variance of the numerator and the degrees of freedom of the variance of the denominator. In this figure, figure 910, it shows the shapes of several curves for the F distribution. Now here is the formula for the F test. F is equals to s squared sub 1 all over s squared sub 2, where the larger of the two variances is placed in the numerator regardless of the subscripts. The F-test has two terms for the degrees of freedom, that of the numerator n sub 1 minus 1 and that of the denominator n sub 2 minus 1, where n sub 1 is the sample size from which the larger variance was obtained. Now, when you are finding the F-test value, the larger of the variance is placed in the numerator of the F formula. This is not necessarily the variance of the larger of the two sample sizes. Table H in Appendix C gives the F critical values for the significance level of 0.005, 0.01, 0.025, 0.05, and 0.10. Each significance level value involves a separate table in Table H. I will be going to show you this table in the next slides. These are one-tailed values. If a two-tailed test is being conducted, then the significance level divided by 2 value must be used. For example, if a two-tailed test with a significance level of 0.05 is being conducted, then the 0.05 divided by 2 equals to 0.025 table of table S should be used. Now let's have an example on how to find the critical value using the F distribution table. Find the critical value for a right-tailed F-test when the significance level is 0.05, the degrees of freedom for the numerator D.F.N are 15, and the degrees of freedom for the denominator D.F.D are 21. Since this test is a right-tailed test with a significance level of 0.05, use the 0.05 table. The DFN is listed across the top and the DFD is listed in the left column. The critical value is found where the row and column intersect in the table. In this case, it is 2.18. See figure 911. As noted previously, when the F-test is used, the larger variance is always placed in the numerator of the formula. When you are conducting a two-tailed test, significance level is split, and even though there are two values, only the right tail is used. The reason is that the F-test value is always greater than or equal to 1. Now let's have another example in finding the critical value using the F distribution table. So when the degree of freedom values cannot be found in the table, the closest value on the smaller side should be used. You should remember this one. For example, if DFN is equals to 14, this value is between the given table values of 12 and 15. There is no 14 in the DFN, so we are going to choose from 12 and 15. And remember that the smaller side should be used, therefore 12 should be used to be on the safe side. When you are testing the equality of two variances, these following hypotheses are used. We must remember that there are 4 key points to keep in mind when you are using the F-test. First, the larger variance should always be placed in the numerator, as what I've stated earlier, of the formula regardless of the subscripts. Second, for a two-tailed test, the significance level value must be divided by 2, as what I've stated earlier, and the critical value placed on the right side of the F-curve. Third is, if the standard deviation instead of the variances are given in the problem, they must be squared for the formula for the F-test. And the last one is, when the degrees of freedom cannot be found in table H, the closest value on the smaller side should be used. Now we have 2 assumptions for testing the difference between two variances. First one is the populations from which the samples were obtained must be normally distributed. Second one is the samples must be independent of each other. So the procedure that we will be using in testing the difference between two variances is the traditional method, which the first step is to state the hypothesis and identify the claim. Second step is to find the critical value. Third step is to compute the test value using the formula F equals S squared sub 1 all over S squared sub 2. Fourth step is to make the decision, and the last step is to summarize the results. Now let's have an example. A medical researcher wishes to see whether the variance of the heart rates in beats per minute of smokers is different from the variance of heart rates of people who do not smoke. 2 samples are selected and the data are as shown. Using significance level of 0.05, is there enough evidence to support the claim? Now, first step, we were going to state the hypothesis and identify the claim. In this case, the null hypothesis will be sigma square sub 1 equals to sigma square sub 2, and our claim or the alternative hypothesis will be sigma square sub 1 not equal to sigma square sub 2. Second step, we are going to find the critical value. We are going to use the 0.025 table in table H. Since our significance level is 0.05 and remember that this is a two-tailed test, hence our DFN is equals to 26 minus 1 equals to 25 and DFD is equals to 18 minus 1 equals 17. Therefore, the critical value is 2.56. And here is our diagram with our critical value 2.56. Third step is to compute the test value using the formula F equals to S squared sub 1 all over S squared sub 2, which our S squared sub 1 is 36 and our S squared sub 2 is 10. So 36 divided by 10 is equals to 3.6. Step 4 is to make the decision. Since our test value 3.6 is greater than our critical value 2.56, we are going to reject the null hypothesis, which means that there is enough evidence to support the claim that the variance of the heart rates of smokers and non-smokers is different. Do you understand, class, how to find the difference between two variances from that example? Okay, if you're still confused or slightly confused, let's have another example. Just like what we did from the previous example, our first step will be stating the hypothesis and identifying the claim. In this case, our null hypothesis is sigma square sub 1 equals to sigma square sub 2. And our claim will be sigma square sub 1 is greater than sigma squared sub 2. Now the next step or the second step will be find the critical value. Here our DFN is 16 minus 1 equals to 15 and our DFD is equals to 18 minus 1 equals to 17. From the 0.01 table, the critical value is 3.31. Now the third step is to compute the test value. Since the given is a standard deviation, not a variance, we are going to square it. So 32 squared all over 28 squared equals to 1.31. Fourth step is to make the decision. Since our test value 1.31 is less than 3.31, the decision is to not reject the null hypothesis, which means that there is not enough evidence to support the claim that the standard deviation of the waiting times of the first hospital is greater than the standard deviation of the waiting times of the second hospital. Now class, do you now understand how to test the difference between two variants? I hope you are now. Now moving on, for finding p-values for the F-test statistic is somewhat more complicated since it requires looking through all of the F-tables that I've shown you earlier, using the specific DFN or the degree of freedom for numerator and the degree of freedom for denominator values. For example, suppose that certain test has a test value of 3.58, DFN equals to 5 and DFD equals to 10. To find the p-value interval for F equals to 3.58, you will be going to find the corresponding F values for DFN equals 5 and DFD equals 10 for a significance level of 0.005, 0.01, 0.025, and 0.05 and 0.10. Then you are going to make a table as shown below. Now locate the two F values that the test value 3.58 falls between. In this case, 3.58 falls between 3.33 and 4.24, corresponding to 0.05 and 0.025. Hence, the p-value for a right-tailed test for F equals to 3.58 falls between 0.025 and 0.05. That is, our p-value is greater than 0.025 but less than 0.05. For a right-tailed test, then you would reject the null hypothesis at the significance level of 0.05 but not at the significance level of 0.01. The p-value obtained from a calculator is 0.0408. Remember that for a two-tailed test, the values found in table H for significance level must be doubled. In this case, our p-value is greater than 0.05 but less than 0.10. For f equals to 3.58. Now let's have an example wherein we're going to use the p-value method. So here in table, our first sample has a sample size of 6 and our second sample, foreign airports, has a 4 sample size. The variance is not given, so we are going to solve for the variance. But first, our first step is to state the hypothesis and identify the claim, which our claim is sigma square sub 1 is greater than sigma square sub 2. And our null hypothesis is sigma square sub 1 equals to sigma square sub 2. Second step is to compute the test value. Do you still remember the formula in solving for the variance? Using your calculator, find the variance for each group. Our variance for the first sample, or the American airports, is 246.38, and our second variance is 95.87 for the foreign airports. Now, next step is to substitute the two variances in the formula to find the test value. Equals to 246.38 divided by 95.87 is equal to 2.57. Now, the third step is to find the p-value in table H that I've shown you earlier using DFN equals 5. Why is it 5? Because our sample size is 6, so 6 minus 1, 5, and DFD equals 3 because 4 minus 1 is 3. Now, here is our table for our p-value. Since 2.5 is less than 5.31, which is our critical value, the p-value is greater than 0.10, and the p-value obtained from a calculator is 0.234. Our fourth step is to make the decision. The decision is to not reject the null hypothesis, since our p-value is greater than 0.10, which means that there is not enough evidence to support the claim that the variance in the number of passengers for American airports is greater than the variance of the number of passengers for foreign airports. Now remember, class, if the exact degrees of freedom are not specified in table H, the closest smaller value should be used. For example, if our significance level is 0.05 and it is a right-tailed test and our DFN is equals to 18 and DFD is equals to 20, since 18 is not in the table, we will going to use the column of DFN 15, the row DFD 20, to get the critical value of 2.20. Now, note that it is not absolutely necessary to place the larger variance in the numerator when you are performing the F-test. Critical values for a left-tailed hypothesis test can be found by interchanging the degrees of freedom and taking the reciprocal of the value found in table H. Also, you should use caution when performing the F-test, since the data can run contrary to the hypothesis on rare occasions. For example, if the hypotheses are sigma squared sub 1 is less than or equal to sigma squared sub 2 written, or it is just the same with sigma squared sub 1 equals to sigma squared sub 2, and our alternative hypothesis here is sigma squared sub 1 is greater than sigma squared sub 2. But if s squared sub 1 is less than s squared sub 2, then the F-test should not be performed and you would not reject the null hypothesis. So that ends our lesson for today's video presentation. Now, to summarize our topic for today, it will be discussed by Teacher Zaira.
Many times, researchers are interested in comparing two parameters such as two means, two proportions, or two variances. When both population standard deviation are known, the z-test can be used to compare two means. If both population standard deviation are not known, the sample standard deviation can be used, but the t-test is used to compare two means. A z-test can be used to compare two proportions. Finally, two variances can be used compared using a f-test.
Today had been a great learning experience.
We hope you all learned a lot from our discussion today.
Just remember, don't stop until you're proud.
Learning math takes time.